Hello, everyone. Welcome to another episode of the Day Zero podcast. I'm Spectre, with me is Z. Today we have some topics on glitching the Wii U, an Adobe Sandbox escape, and a Windows Bluetooth Vuln, as well as the Spot the Vuln solution, which I'll let Z get into here.
Yeah, this week's Spot the Vuln is kind of a web app one. Well, it is definitely a web app issue. You can see the code here. We've got a couple routes to find. This is a Python application. Uh, Presumably Flask, but I don't really depend on much that's super. I guess I do call JSONify, which is definitely a Flask thing. But I mean, app.route can be generic enough. You've got, the two routes, register and some admin sensitive action. Sensitive action does the if not is admin, makes the call off to just JSONify unauthorized and does HTTP 403. So the whole goal there is, can you get through that is admin check somehow? Some of the other code in here, we've got token generation, so there is some sort of, it's not a JWT. Instead, what we've got is and unfortunately, kind of trying to compress this code down does make it a little bit rough to read. Some of these long lines here, but yeah, it takes a random user to generate a token for this user. It will basically join them with a double underscore. So takes like the user ID underscore username underscore whatever their user level is. So user, admin, whatever. It'll sign it. That's just kind of a magic function that, again, adds underscore and the signature. Later on, to verify that token, it splits it on the double underscores, grabs the signature, and, verifies that it signed the data. I abstract those down to a couple functions because how it does the verification doesn't matter. That isn't the vulnerability here. The vulnerability is actually down in the registration route, or the core vulnerability, where it does this regex match. So on the username, it checks start of strings start of line with the caret has a character class from capital A dash lowercase c. So in theory, you're matching from the capital A down to or up technically to lowercase z plus to, and the character case there have multiple of them. $sign saying like you have to match the entire string. So with caret and $sign, you're matching an entire line there. If it's not the entire line, so if there's any characters that don't fit inside of that A to Z group, then it won't match. So effectively, it is, or at least the thought here is that it will match only if the entire string is alphabetical characters. But the problem is, capital A to capital Z, that'll work how you expect. But by doing this capital A to lowercase z, that's kind of it's not always a vulnerability. In this case, it is. Let me pull up an ASCII table here really quickly for those here. The way regex uses the dash character is it has no real concept of I guess there are the I think it's a backslash code or whatever, I don't know what it is for alphabetical characters, but there's probably one of them, like /W or something. I don't know regex well enough to remember. That's specifically matching like that character class. But in general, when you're using the dashes, it's basically saying like for A, it's saying, start at hex 41 dash and go all the way to hex 172, or sorry, 7A, hex 7A for lowercase z. And it's matching all of the characters between there. And that includes all of these special characters in the middle. So because that ends up including the underscore here, you can include underscores as part of your username, which then means you can kind of inject the user level yourself and gain control of it that way. So the core issue is really that regex thing. I don't even want to call it a quirk of regex, but it's something that's easily misunderstood if you just go and try, like you're like, oh, I need the characters A to C, and oh, what if I use the lower? Oh, that works too, because you give it some tests with a few random characters, you might not hit exactly the ones that will still match on. So unless you really understand how regex works, it's really easy to make that mistake.
It's sort of similar to a past spot the Vuln we had with the asterisk character. Or sorry, not the asterisk, the dot character. So have like using it for validation of a URL. You just put a dot in there, assuming okay, I want it to match like x.com or whatever, not realizing that that could be any character, and abusing that. Things that seem fairly intuitive just looking at it, but when you dive into what the regular expression parsing is actually doing, um, could contain issues because of how the actual parsing is working on the back end.
Yeah, exactly. And this is actually similar to another spot the bone that had the same idea of kind of injecting something into the username to manipulate the token. It's just kind of an easy idea to toss in here for, I guess, those sorts of string parsing issues.
All right, so getting into topics, kicking off with a fun one, we have Shiny Quagsire's post on glitching the Wii U via OTP Fuse contents. So this is a little bit more on the hardware side than than what we typically cover. That said, I also really like this area of research, and so I still wanted to talk about it. And console hacking is always fun to talk about. What actually kicked off this research was the fact that some Hynix Wii U eMMC multimedia cards were degrading and starting to fail, which might not sound like a huge issue. Just replace the media card, right? Um, the thing is, the firmware is stored encrypted on the media card, and it's also per console encrypted. There's a personalization layer going on there, which uses a key that's in the boot ROM. And the contents of that boot one package that gets loaded is also verified against a hash stored in fuses. So if that hash violates, then it'll brick. It won't be able to boot, and your Wii U is bricked. Um, Now, I think we've talked about fuses maybe a few times before on the show, but for those who aren't familiar with what they are, they're very similar to in real life fuses if you've ever had a house that used them or whatever, except they're extremely tiny and on die. And the idea is you can choose to blow these fuses at a given point in time to store information. So, like a blown fuse might represent a 1 and an unblown fuse a 0, or vice versa. I think it's typically, the first way. And it's very useful for encoding information that you want to be black boxed and not easy to extract, such as like encryption keys, or just having something that's more immutable, like the SOC ID or anti-rollback type stuff, anything like that. Anything that's somewhat sensitive.
So, can
So,
you actually expand on that slightly on the being hard to read aspect? Because not that I'm doubting you about it. I'm more familiar with Fuse in the sense of it being something that is meant to be immutable. So you've blown the fuse, you can't unblow the fuse, or at least you can't do that usually in a very easy way. But are they also just more difficult to read? Or like what
so
aspect does that?
it kind of depends on the target and how it uses it. Um, but yeah, like the idea is you can only really read the fuses in certain areas of code that are like really privileged and not easy to access. So for example, on like AMD CPUs, there's some stuff like sensitive information that's stored in fuses. The only area that's able to access those fuses is the PSP itself, which is considered trusted. You can't just go in like the x86 kernel and MMIO to those fuses or something. They're kind of managed at a higher level, I guess, a higher trust level.
Okay,
So
yeah,
that's
that
kind of the idea with keeping those contents secret.
yeah, that makes sense. I mean, it would also just kind of take, I guess, a different interface to read it, so it's not like you're going to just get access to it in the normal ways anyhow. So yeah, that makes sense. I just hadn't thought about its usage in that way before.
Yeah, it's a bit more common in like consoles, I think, than some other products. But yeah, storing encryption keys and stuff in fuses is not too uncommon. So yeah, the main thing that's important here though is the hash that's stored in fuses, which is used to validate the boot. What's interesting though is if the hash is all zeros, the signing is basically disabled, and it'll load whatever from the NAND. So being able to glitch how these fuses are interpreted is a very lucrative target to look at, because not only could it be used for potentially bypassing having a Wii U console bricked, it's also interesting for running homebrew, for running a custom boot package, and a custom operating system and whatnot. So that was the basis for this project. He goes into some details on how the fuses work. Typically, with fuses, you'll have like a sense and burn circuit. The sense circuit will run a bit of current through the fuses, and if it completes its path, it's unblown. The fuse link is there, and when it wants to blow a fuse, it'll drive a large amount of current through it to burn the fuse link, and future senses, of course, won't be able to make it through. Which is how you have that one-time programmable aspect. You're not going to be able to repair the fuse once it's been blown. And typically you'll have banks of these fuses. The Wii U specifically has like 8 banks of 128 bytes, so it has 1024 fuses on die. And yeah, so these are sensed on boot and they're read into registers for things like verifying the boot process. So the idea was glitch that boot process to get these fuses incorrectly sensed to zeros to disable that signing and run a custom boot one package, which power glitching kind of makes sense for, right? As you can make the current that goes through these fuses low enough in the sense phase that you can potentially make it incorrectly assume that those fuses are blown or whatever. So they go through a lot of the details here on setting that up, even managing to find like a debug GPIO they could wire up. Initially, they tried doing some power, some power and reset glitching, which involved holding reset and inserting a very small reset pulse at a delayed offset, hoping to trigger something like a partial reset situation to see if there could be some interesting behavior they could trigger. It didn't really work out too well. They were able to bypass the signature check and get to boot one, but boot one wouldn't actually execute. So it was a bit of a weird situation, which it's pretty common when you enter these hardware glitching scenarios. But yeah, so then they decided to try combining the reset glitch with undervolting, and that actually did have a bit of success. They were able to get what I assume is a debug code flashing in one instance. I say I assume because they say I pressed the button, I wired to reset, and was greeted with a success trigger, hex 88 flashing on the debug LED GPIOs. Doesn't really go into detail on what hex 88 is though in that context. But yeah, and after enough messing around, so that specific case, they did manage to hit it once, but they weren't able to reproduce it. But that was kind of an indication that the strategy probably could be tweaked to work. And yeah, with enough messing around, they were able to cause a brownout when the one-time programmable fuses were being read into registers and got them to read as zeros instead of their intended values. So using that, you could boot into like custom firmware. On top of that, there was also this funny bonus where the static RAM or SRAM on the chip wasn't being cleared on reboot. And so because of that, they were able to kind of brute force the boot one key when it was being used to decrypt the firmware off the multimedia card. So yeah, I mean, some very cool research here. There is the open source mod chip project that was put up on GitHub. That'll be in the show notes, and it also just links off from the article. I'll bring it up on stream here too. As the post points out, it's not super user friendly. You would need an FPGA, and the components and such aren't standardized. It also hasn't really been tested on other consoles, so the glitching parameters might not be standardized either, because there's some variance with that. Some different models or different iterations of the same model might use slightly different components, or different ambient factors might factor into the glitch parameters. But Quagsire is welcoming collaboration on this, so it could be a really cool project to get into if you're looking for like a console related project. It probably would need, like, especially where it's so rough at the moment, you probably would need a good amount of experience in hardware hacking and knowing how to use like an FPGA and whatnot. But yeah, I mean, it's a really cool project. And it's just a really interesting area of research. The Wii U is obviously a bit of an older console. I don't remember exactly when it came out. I think it's been like 10 years or something. But even still, it was a console that people liked, and the Nintendo consoles in general are somewhat timeless. So it's it's a really cool research project, and I'm looking forward to seeing if some more stuff comes out of this.
Yeah, in terms of a post, also like goes pretty deep. But there's like a lot of information here that I kind of appreciate just sharing the research, even if it is kind of just a Wii U or older console.
Yeah, I mean, I kind of skipped over it in the interest of not going too deep, and some of it I don't fully understand also. But yeah, it even goes as deep as like the frequency, like the clock rate at which the fuses are being read. So there's a lot of cool information there as well, for sure.
Yeah, and just complete side note, but I did notice this was a Tumblr blog. I don't think in like all of our episodes we've ever had a Tumblr blog up or any of these.
I
Like,
didn't
because
even think about that.
Tumblr is not somewhere I think of like, oh yeah, let's go check the reverse engineering or exploitation Tumblrs.
Yeah, it's a funny call out. I didn't even think about it, but yeah, really cool post, and I do recommend checking it out if you're into console hacking stuff. All right, so getting into some more of the classic style vulnerabilities we cover, there was an SSD disclosure post on an out of bounds write in SonicWall, which is like an enterprise firewall. And Z, I'll let you take this one.
Yeah, this is kind of a fun vulnerability that I can definitely see how a developer would make this mistake. So, for things, Spectre just said it's enterprise firewall. So, part of what they do here, they have the HTTP server function. It does a little bit of string matching on like the paths coming in. Specifically, they call out the slash stats slash and slash security underscore services slash. Actually, it's just looking at the path that's coming in. Does it match something? I am assuming that it's working like a reverse proxy given what it's doing. Because what it does, if it matches one of those, it then creates a request line. It takes the verb from the line, tosses it into it, or prints it into a new one, takes the path, prints that in, gets the HTTP version, prints that in. So it's like it's creating the request line, presumably because they're going to format this into like a new request going out there. But the way it does it has a fun little vulnerability in that they use snprintf twice. Presumably they have a 1024 byte buffer. So they're calling snprintf, and the first call to that is just with this %s. So that is the HTTP verb and the path that they read. And they're going to print that into the string, which is presumably 1024 bytes. Because what they do on the second line when they're writing the HTTP slash, so the version, they take 1024 minus the return value of snprintf from the first one as like the maximum number of bytes snprintf can use. I feel like most of you are probably familiar with snprintf, but if you're not, it's printf, print formatted. sprintf, instead of printing to screen, it'll print to a string or into your buffer that you provide. snprintf, you can say, and the buffer is this many bytes, so it won't print more than that. So they adjust the end value to basically subtract what they've already written into it. Makes sense. Fairly intuitive way to go about it. But, and this code would actually be not fine because you have kind of the issue of sprintf not knowing string lengths. But this code would do kind of what they're thinking of if they were using sprintf. There are other issues, and you don't have the maximum value going in there, but if they were doing this with sprintf, because sprintf returns, the return value of sprintf is the number of bytes written to the buffer. The return value of snprintf, which is the value that they're taking when they're calculating the size of the buffer for the second snprintf, they're using the return value. Instead of actually that printing how many bytes were written to the buffer, it prints how many bytes it would have written to the buffer if the buffer was large enough. Which means if you give it a very long path, something greater than the 1024 bytes, snprintf will return saying, hey, this string would have been 5,000 bytes or something. I think that's getting too large for the HTTP spec, but some large number would have been this large. And then when they go into that second one, that snprintf call, 1024 minus 5,000, well, that's going to go negative. That's going to wrap around. And you're getting kind of a overflow type of situation there. And so snprintf is no longer having appropriate bounce checks, so that next call into snprintf is going to overflow the actual buffer because it can copy way too much data. In terms of exploitation, this is happening on the stack, but there are stack canaries, so they call this out as just leading to a denial of service condition by overflowing the stack canary. Seems likely that that's probably going to be all you're limited to in this case. Um, but yeah, I don't know. The whole SN thing and the difference between SPrintf and SNPrintf is kind of a really critical detail that is super easy to overlook and just forget about, especially if you're updating code to be like, oh, we were using SPrintf and like percent with the sizes in there. Let's just move the size out and like do the calculation like this. Like it makes sense to think about that way, but it doesn't actually work. It's just a really subtle difference that can introduce bugs.
Yeah. It's worth noting that they were only able to get like a denial of service with this overflow, because basically what you end up getting is a pretty large stack overflow here. It is a stack buffer. The crash happens because you hit stack canary. So that's the reason it's a DOS and it doesn't seem immediately exploitable unless you can leak that canary with another bug, or maybe not even, depending on how the canary is structured. Like if it has null bytes in it, then you probably won't even be able to do that. You won't be able to attack the return pointer or something. There might be some other interesting data on the stack that can be hit before the canary. That said, it's really dependent on like the state of the stack, and I'd be willing to take SSD Disclosure's word on it and assume there probably isn't any other interesting corruption logic targets. But yeah, I mean that is worth noting that they were only able to get a denial of service. That said, when you're talking about a firewall, maybe that is somewhat significant. Maybe you could do something with that as an attacker.
Yeah, I would guess that this is unauthenticated also to the firewall. I mean, it is going stats or security service, but I'm guessing offline's on that side.
Yeah, I don't
Like
believe they say. They just say remotely. I don't think they say if it's like authenticated or not. That's a fair point, though.
yeah, I would assume so, given what I've seen with
Oh, sorry. They
they do
do.
call it out. I missed
Yeah,
it.
second sentence at the top. They say authentication is not required to exploit it. So there you go.
Oh, way up there. You know, I just scroll right to right to the analysis.
I know that's kind of what I tend to do too. So that's why I didn't. It didn't pop into my head immediately. But yeah. So yeah, maybe it could be useful in that context. But yeah, like it's kind of a straightforward vulnerability, like it is, an integer underflow. But how it happens and the context around it, I thought was pretty neat. How it worked with the SNPrintf and uh, having that sort of second stage to it to be able to exploit it.
Yeah, it's also kind of a bug class that I completely understand how a developer could introduce this, but I don't think we've seen it too often.
No, not really. It's surprisingly rare that we see it in the show in this sort of way. Yeah.
Sorry, I definitely said that wrong, but asks, is there a good reason all these embedded devices seem to roll custom HTTP services or servers? Like why aren't they using open source tested server like mini HTTPD? There probably isn't a good reason. Not made here syndrome type of deal.
That's exactly what I think it is. Yeah. I think it's not
I
made here.
see that. I could see maybe licensing being a consideration, but not really a good reason. APR harder to hide backdoors. I mean, but you can easily go ahead and patch your backdoor into something open source. Um, because assuming you're
Depending on the
compiling
license.
it, like if you're dealing with a library, it is a little bit harder because then it's easier to diff just a library like the SO binary or something. But if you've got the code there, I mean, diffing is still going to be a bit of a pain. I feel like it's about as diff or about as easy both ways. My opinion. I haven't really done a lot of that to try and track down the backdoor, so I am just kind of making things up as I go.
It's not super relevant, but the other thing that could matter with that too, just as for fun to talk about it, is the licensing. Because if it is a license that requires you to state changes and disclose source still, then yeah, it would be harder to hide the backdoors. But yeah, it kind of depends on the license, which you touched on earlier. Yeah, I mean, with these IoT type devices, I vaguely recall one recently I looked at where it was just like, oh yeah, somebody wanted to roll an HTTP server and we just kind of ran with it. Like it seems very much like it's just, yeah, don't want to deal with someone else's code base, and so we just rolled our own. Um, And like I feel like rolling your own HTTP server is starting to fall into like the don't roll your own crypto category, because it's like HTTP. There's just so many things you have to deal with, especially if you start dealing with like HTTP 2 and like different versions of it beyond 1.1. Um, I don't really understand it. It feels like you're inviting future headaches in by doing that, but it does seem to be a super common thing in the IoT space for whatever reason.
In fairness, how many of these actually do HTTP2?
I don't think I've
I
seen
don't.
many.
Yeah,
Yeah.
I feel like a lot of them do take some shortcuts when it comes to it. I feel like the most likely reasons here are just licensing and not wanting to use like third party products at all. So like the not made here idea, which is kind of common in like a lot of corporate environments. So I would assume you'll see it in these IoT. Well, I guess this is. Oh no, routers are somewhat IoT.
I fit them in that category, but
Yeah,
yeah.
like they're embedded like small devices sort of deal. But I do feel like it's separate also from Internet of Things, where it's like it's not a smart TV. It's a router. It's meant to be a little device. It's yeah, whatever.
Yeah, kind of pedantic, but um yeah, I mean it's interesting to see though. Like I will say, seeing the custom HTTP servers, it does give us stuff to talk about. So you know, because that is a fair source of a good number of the topics we cover is these custom rolled networking or HTTP servers. So yeah, I guess I won't complain too much. Yeah, but with that out of the way, I guess we can move into our next topic, which is out of Kihu 360 and is a bug and another integer overflow essentially in the Windows Bluetooth bus driver. Ultimately, the bug comes down to an issue in the Service Discovery Protocol or SDP record area of the driver, which can be interfaced with from user space via ioctl. Since these records are somewhat opaque and can contain different types of data. It has the kind of typical structure you see where your header, you have a header, a data field, and like a type and size descriptor. The problem is when querying for attributes inside of the ioctl, they take the size and accumulate it for allocating a buffer to hold the attributes that you're querying, and they don't check if that can overflow. So later on, that size is added to like some other unknown variable they don't label in decompilation +1, and that's passed to x allocate pool with tag. So yeah, they use that size, add to it for the allocation size, which can lead to an overflow of the integer, lead to a small allocation, which then later on, when it's actually used, can go out of bounds. Fairly straightforward, integer overflow type issue. This would be a heap overflow in the kernel pool, and it would be a fairly large one at like 4 GB. So they did need to take some care on which pool they would hit. Ultimately, they chose the segment alloc pool, which can span 4 GB in size, and they also leverage the named pipe technique, which they don't really go into here. They do link off to it, like a GitHub repo that explains more about how that technique works. I won't go super into it, but it's fairly like on the label of what it is. You attack named pipe control blocks to derive read-write primitives by forging data queue entries. It's just abusing the common Windows structures for a read-write primitive. It's nothing too crazy. So yeah, they were able to get arbitrary read-write from it, I believe. Um, they say towards the end that they put a lot of effort into making it stable, but they say it's still not 99.9% stable, but I don't think they actually go into how stable it is. So it's a bit funny, because I would be curious on when you're trying to hit these very large pools with a very large overflow, it seems like something that can be very prone to failing. Hitting like just not getting the right allocation, missing the timing, and hitting something that you can't fix and blowing up the system. But yeah, I don't think they really comment on that too much. But yeah, fairly
Yeah,
straightforward bug and overflow. If you want to know more about the technique, though, yeah, it's not really in this post. You'll have to go to the GitHub for that.
yeah. I'll toss in one really slight clarification. The overflows with the in the service discovery protocol, you're able to query for the services, and then you get the entire like the entire service record comes back to you. So if that service record contains large attributes, which is an attacker controlled thing, you don't basically, you're not querying the attributes despite how they explain it there. The query is for the service. um kind of a nitpicky thing, but
Fair enough, though. Fair clarification. Yeah, we'll get into our last topic here, which was posted by Exodus and is another integer overflow in the Windows crypto provider. So Z, I'll let you take this one.
yeah, a lot of into overflows for this episode, which is fun because it is one of those bug classes where, despite the fact that these are all starting with int overflows, like an int overflow can lead to a number of different primitives depending on what the integer is doing. The first one's the buffer overflow. Second one, ultimately we get to a buffer overflow, but it's because of a small allocation. You're overflowing that allocation size. Anyway, so getting in on this one though, where the vulnerability is, it's dealing with the Microsoft cryptographic provider, and they're inside of the Adobe Sandbox. They have some vulnerability inside of the sandbox, and this is kind of being used to escape the sandbox. Post itself goes into a little bit about how the sandbox works, the sandbox broker, and the actual sandbox application. So when the application wants to access any sort of file system data, anything outside of the sandbox, it goes to the broker, it asks for that, broker sends it back. Does that using has like a 2 megabyte in size, a piece of shared memory. It'll write its message into there, send a signal to the broker saying, hey, there's a new message. Broker reads the message, does whatever, writes the response to it back into that shared memory. They kind of have set up addresses. They talk about the actual memory layout for this. In there, or later on in the post, but ultimately, like, the idea is shared memory signaling back and forth to say when they're actually done. And Sarsec also mentions, I read this article, but I couldn't figure out if the overflow was patched or not. That's a good point. I read this assuming it would be patched, given kind of what Exodus does. I can't imagine they'd be like burning a live vulnerability.
There is an MSRC security advisory around it, so I would venture to say it's patched. They say it's present on multiple Windows 10 versions, but yeah, like I was just looking through the MSRC when I saw that comment. So
yeah, and I guess there's a CV reported, but that doesn't necessarily mean it's patched. Either way, I'll stick with what the vulnerability is. So one of the features here with the sandbox is you can make some of these crypto calls. Tell the sandbox you want to do whatever. And the vulnerability itself is inside of this. Let me just find the function here. Import opaque blob. So when you're like importing a key, that's just going to be treated as an opaque blob. So just a black box. It's a bunch of bytes, a bunch of numbers. You're going to import that. So you get access to this through the broker. You get access to calling this crypto or crypt import key method of the crypto service provider. And inside of that, I'm sorry, I kind of have to gather my thoughts a little bit as I'm going through this one. It reads out 2 values out of the blob or out of the structures being sent in. One of those values is at offset hex 10. The other one is at offset hex 14. Ultimately, what matters is that these are really just working into the size that gets allocated. For some reason, I'm trying to find the code for that. There we go. I was looking at the wrong code block. You'll see here it goes. This first one here reads out at plus 14, the other one plus 10. Ultimately, both of these, if they're set, end up incrementing this V8 value, which passes into the continuous alloc. So these values, though, that are being read, V13, V14, both of those are attacker controlled values. So again, you kind of run into that into overflow situation. If you provide a very large value, then when you do these additions, it will overflow, it'll wrap around, you'll get a very small allocation, and then later on when it's copying the data in, it's just going to overflow that buffer. So core vulnerability, again, we're ending up in kind of that buffer overflow situation from this. But what I thought was really interesting was on the exploitation side, and on that side, they kind of talk a bit about what their overall strategy was. So again, they're inside of this Adobe Sandbox. They're able to hit some of these crypto functions through that. But it is a sandbox, so it does have the expected security features. They mentioned here ASLR, but they also have control flow guard in place, so that's preventing them from hitting like just a standard ROP chain. So as a bit of background here, you've got the crypto service provider that has like a context object. Ultimately, all of these functions that you're able to call, those are all just various fields inside of this inside of that context object. It just has the function pointers to verify signature, generate a random value, whatever is going on here. You're just able to, or it just keeps these function pointers to them. And when you invoke one of the crypt SP or the service provider functions, it will figure out which handler it's actually supposed to go out to, and it'll do a self call on that. Also, one of the interest points here is inside of the object, there is the encrypted crypto provider object, which is an encrypted pointer to the actual object they're calling these methods on, which adds kind of a little bit of an extra challenge into this exploit because they can't just overwrite the pointer to somewhere that they want. It needs to be this encrypted pointer, so you either need a way to encrypt it, you need a way to leak encrypted pointers. Sorry, not a way to, like, you need a way to sign or like create your own encrypted pointers if you want to use that, or you need a leak one to reuse it. Or I'm sure somebody has some other creative ways, but that's your main idea on it. So basically what they did with their overflows, you can overflow into, or ultimately you can kind of get through some of this into some of this data and actually corrupt one of these. But even if you corrupt one, you still need a way of knowing, hey, which object did I corrupt? Like, where is it in, or not where is it in memory, but I guess I kind of missed the fact they are doing some heap spraying here, having multiple objects, then you need to figure out which one was corrupted using the heap spray, so you kind of have multiple chances going on there. And what they do with that is they basically just target the gen random function pointer, point that somewhere that's just going to return a constant value regardless of the argument. And then they can just go through all their objects, call the gen random on it, and see, hey, which one is giving us the basically canary value, which one is not working how it should, and that's how they can know this one has been corrupted and kind of figure things out from there. So they use that object or that call to identify which things they're corrupting. Kind of hinted towards this already, but maybe I should have laid it out. Because this thing's doing self calls on, so it'll call the CP, whatever these functions are, with the encrypted pointer. And I keep saying self calls if you're unfamiliar with it is kind of close to a C++ thing, I guess. Self calls, like if you're familiar with like CDECL calling convention, fast call, all of that. Self call is another option. And that's used with objects. You're calling a method on an object, so you need the pointer to that object that you're calling the method on also. So basically, it works very similar to other calling conventions, but the first argument is the pointer to the object. So in this case, the first argument is going to be the encrypted crypto provider object. So anyway, all of that said, what that gives is when you control one of these pointers, you're getting that function called with kind of a.
I
Okay,
would call
so
it a
it's
gadget.
yeah. You're getting any of these functions called not with the actual value that you've like the encrypted pointer is going to be decrypted when it's actually used as a pointer. So you're not actually getting control over the second argument exact or directly or the first argument, but it's calling all these functions with the first argument that is somewhat controllable. Like you could control it, but you do need to have it as an encrypted pointer. So it has that restriction on it. So the way they kind of go about doing this whole attack, so they have that method called arbitrary functions, just with that kind of requirement or restriction on it. The way they end up chaining everything is they will corrupt one object and put the arguments they want to use in it. So, basically, they want to put the function pointer to WinExec somewhere in there, and then they will use. Okay, allow me to try and rephrase that. I'm sorry for kind of jumbling around or jumping around a bit on this post. I should have tried to have a better summary ready to go, but the way they're getting or the way they're actually abusing the encrypted pointer is by corrupting two objects. One of the objects, when they corrupt it, they've changed the start of the object to be whatever argument they actually want, whatever string value they want to start. They're ignoring all those function pointers. They don't care, or they don't matter. They're just overriding it with whatever data they want at the start, to be at the start of it, and then they're able to use the pointer to that object as the encrypted pointer in another object. So when they corrupt a secondary object, they give it that encrypted pointer that goes to that first one with like the argument that they want, and they'll overwrite something for the function pointer so that goes to WinExec. So then when you call the function that basically dispatches these all out, when you get that call to happen, it will take the encrypted pointer that they leaked or stole from the first object, use that as the argument to the function call that they also now control through corrupting the function pointers, giving them this arbitrary function call with the controlled first argument. So they can use that call WinExec with a controlled first argument and gain code execution with the privileges of the Sandbox broker. I thought
They're
it was
basically
really
like deriving their own signing gadget in a way. Being able to like forge that data and indirectly get an encrypted pointer to it. It's kind of neat. It's sort of similar to some of the pack stuff that we talked about some time
yeah
ago with Apple.
yeah it really reminds me a lot of that. Not really a signing gadget exactly, but like they're reusing an existing already signed gadget, or they're reusing an already signed pointer for their argument. So a little bit different from the signing gadget concept, but yeah, it has kind of that pack vibe. But yeah, I thought it was a really cool post. Despite me fumbling this, I think I thought they did a really good job actually describing the exploitation section in here. And they do go more. I've focused really on that exploit tragedy. They do go a little bit more onto the spraying and all of that. I've glossed over several aspects of it. They go into quite a bit of detail. I thought it was pretty well done at that aspect. The vulnerability aspect, I had to kind of scroll up and down. And it's very spaced out, very annoying to deal with. But when it came to the exploitation, I thought that was a really interesting aspect. I haven't really seen that approach for. Actually, I haven't even seen Windows apps with the encrypted pointers, but that might just be the fact that I'm not doing a lot of Windows stuff. So that was kind of novel to me.
Yeah, I guess it's like a software implementation of like pointer authentication. It's a little bit interesting. I didn't really know that Windows leveraged that either. But
Yeah, I'm
again,
not
it's like you, I
sure.
don't really do much Windows research, so
Yeah, I'm not sure exactly how that's being implemented here, how that's working. I was hoping the post would go into it, but they basically just say encrypted pointer. They don't even make it clear that that's like um how they're getting around, like they're reusing it and stuff. Like, oh no, I feel like they don't indicate the problems that creates. They just indicate how they deal with them. If that makes sense. So yeah, the encrypted pointers are mentioned 3 times in this post. It's not very much, but that aspect I did think was the most interesting aspect of the post.
Yeah. Another aspect I wanted to bring up a bit, when you were talking earlier about abusing the cryptgen random function pointer to identify which object, is being used, to get a predictable return value. Um, it's something I wanted to bring up because of the fact that CFG is in play here, control flow guard. So we've talked about it a few times before when CFI has come up, but there is like varying degrees of enforcement of CFI. You can have more of like the coarse grain CFI where it's like it has to be a valid function, but any function will do. Or you can have the more fine grain CFI where it's like it has to be that function. If you try to change it to a different function or some other subsystem, it'll blow up.
Yeah, I
So that
think
is kind of relevant here.
most fine-grained CFI that we see is signature based, so it's looking the functions have to look roughly the same. I don't think we've seen any implementations that are actually needs to be this exact function.
Yeah, Clang-based CFI, well, you can actually configure that too. But generally, where you see the more strict CFI is that. But yeah, I wanted to point that out because it is highlighting one of the various bypasses around CFG, is being able to use function level gadgets. That is essentially what they're doing there for that technique. Um, Something else that I was thinking about when we were talking about the vulnerability is the vulnerability comes from adding these values in the opaque key blob. I wish they went into a little bit more detail on what those values actually were, because it kind of ties into something I mentioned in a recent topic we had that was crypto related. Various different encryption schemes can be kind of tough to deal with from a code perspective, unless it's like a straight up, like AES is kind of simple to deal with. You have known key sizes. You can have a few different key sizes, but the key sizes are known, size of data is known. But then when you get into things like RSA and you have like exponents that might not have like a known size, it gets a little bit trickier. I would be curious on what the context was around this code. They don't really delve into that because I guess it's not super relevant. What's important is the fact that they are added together and used for this allocation. But on a personal point, I'd be curious on what these values were being used for here, and kind of tying into chat. I think Starsec or IAPR mentioned earlier. I don't remember. My chat got cleared, but somebody asked like how this vulnerability was found, whether it was through fuzzing or code review, and I think knowing the crypto scheme that was being used there would help hint toward that. Um, yeah, I would assume maybe fuzzing. This seems like a very fuzzable bug, something that would come up pretty quickly. I don't think you would need to do like a thorough code review to catch this, but yeah, I don't think they mentioned that in their post. Unfortunately, only Project Zero really goes into like how they think things might have been found. I don't really see other security firms or anything talking about that.
I
Unfortunately,
mean, researchers on their own blogs will indicate it, of course, but no, I
sometimes.
yeah, not always, but that's usually where I'd see that information is if they're documenting their own process of finding and their own exploitation. Yeah, I agree with you. I feel like this is probably a fuzzing bug because it is just large values in 2 places leads to bug, and leads to obvious overflow. Like there isn't a lot of subtlety to this that would make me think it's complex or really hard to reach. The only restriction on hitting the code path, if you call in there, is like the length of what's coming in has to be at least hex 70 bytes. So like not a very complex restriction here. Reading, like I agree with you on wishing they'd indicate what the values were, in part just to read this a little bit easier, because especially like hex 14 and hex 10 are very close together, so it's not like you can't just glance and know exactly what they're talking about. Because throughout this, they just refer to it as, they read the value at unsigned or cast to unsigned in, cast to U and A to T, key plus 0x14. Like they always refer to it in this massive way, but that's a writing thing, so whatever. But Yeah, I don't know what the values stand for. That's kind of the challenge on Windows is you're dealing with a lot of black box. Just it does this, it reads this value, and why it reads the value, who knows?
You'll have to figure that out if you care enough. Yeah.
Yeah, I mean,
Um,
unless what is it, React OS? Um,
uh, oh, you're talking about the like reversing Windows
IONSQ's
project?
thing.
Yeah.
Yeah,
Yeah, React. Yeah.
yeah. I mean, if the structure is in there, you get a bit more information.
Yeah. Which again is why like this low hanging fruit bug, I feel like it probably was found through fuzzing. Because it's just a lot nicer to fuzz Windows stuff where you don't have the source necessarily. And especially with crypto, crypto stuff can be a bit tough to go through and dig into, and it's something a lot of people just want to wave off, like, oh, okay, I'll just pretend that's a black box. It's encryption. I call something. I pass in decrypted contents or plain text and I get encrypted, like whatever. It's very a lot of people just don't want to deal with it. So it's not surprising seeing an issue like this come out of the crypto subsystem. But yeah, I'd be curious on exactly which. Actually, hold on. Sorry, they do kind of hint towards it actually, because at the screen, like at the part that you have open now, they mention the various libraries that are used, like DSS for Diffie-Hellman or DSA, RSA, base CSP for smart cards. They say that this comes out of the RSA package. So yeah, this probably was like the exponent and having to deal with like the unknown data sizes for the key importing. Yeah, so it is an RSA. Fair enough. I just didn't really put two and two together immediately. So
Yeah, fair enough. I didn't even think about that as he was asking it. We'll also mention, I guess, part of this. We describe a method to exploit a Windows end day. So it's possible this was like they weren't even either the author wasn't even the one to discover this, so we can't really speak about how it was discovered, or they can't really speak about how it was discovered. It could just be the case that this was something that they're like, this would be a good candidate for somebody to provide, which is something Exodus does. They have like a bounty for doing end day exploits.
yeah, they have kind of like a hit list or an interesting list that they would take reports for. So yeah, it could have came out of something like that too, for sure. But yeah, fairly interesting posts all around. A lot of integer overflows as you touched on earlier, but the context around them and the way they were exploited is pretty neat. And we had a little bit more Windows than we typically do. So yeah, unless you have any last minute parting thoughts, see, I think we'll go ahead and wrap up the episode though.
Yeah, no shoutouts this week.
All right. So as always, thank you everyone who tuned in. If you want to catch any past episodes, you can find recent ones on Twitch and all of them on YouTube, Spotify, Apple Podcasts, and more off of Anchor. We also have a Discord and a Twitter. Feel free to follow us or join us on those. Links for those are down below or in the chat. We also have the Spot the Vuln threads up on there as well. If you want to check out any of the past ones or some of the future ones, if you want to take a hazard a guess at some of them before we cover them. But yeah, with that said, that's everything that we have for this episode, and we'll see you next week.